lecture presents an implementation of the abstract data type bag using an array data field to store the items in the bag. When you use an array to organize data, the implementation is said to be array-based. In future lectures, we'll present another approach to storing data in a collection. Earlier, we developed a Java interface for the ADT bag, the interface bag interface. Each public method within the interface corresponds to an ADT bag operation. Our array-based implementation is called ArrayBag to indicate the type of storage used in the implementation. We'll use the same generic type T in the definition of ArrayBag that was used in our bag interface. The definition for the class ArrayBag could be fairly involved. The class certainly will have quite a few methods. For such classes, you should not define the entire class and then attempt to test it. We begin by defining the data fields. We already know that one is the array that stores the items in the bag. When working with a class, the constructors are implemented first so that the data fields can be initialized before any methods are called. Next, we identify a group of core methods to both implement and test before continuing with the rest of the class definition. By leaving the definitions of the other methods for later, you can focus your attention and simplify your task. But what methods should be part of this group? In general, such methods should be central to the purpose of the class and allow reasonable testing. When dealing with a collection such as a bag, you cannot test most methods until you have created the collection. Thus, adding objects to the collection is a fundamental operation. If the method add does not work correctly, testing other methods, such as remove, would be pointless. Thus, the bag's add method is part of the group of core methods that we implement first. To test whether add works correctly, we need a method that allows us to see the bag's contents. The method toArray serves this purpose, and so it is a core method also. Similarly, any methods that a core method might need to call are part of the core group as well. For example, since we cannot add an entry to a full bag, the method add will need to call isFull. Once the core group has been implemented and tested, additional methods can be implemented and tested, either one at a time or in groups of related functionality. To decide which data fields we need in our implementation, focus on the activities that the interface requires us to perform. We begin by using an ordinary Java array to represent the entries in the bag. With this implementation, your bag could become full, just as a grocery bag does. Another lecture presents an additional implementation that does not suffer from this problem, giving us a bag that is never full. Here we have our array and 5 names we want to store. When items are stored in our bag, we can place them in consecutive array elements. Storing the items in consecutive array elements helps with the bookkeeping necessary to manage our bag. Now suppose we want to remove Ted from the bag. That array element becomes vacant. If we still want bag entries to be consecutively numbered elements, however, one entry will need to move into array element 2. Since the bag entries are not in any particular order, if the entry in the last field element moves into the vacant element, no other elements need to move. We can continue to add new items in the remaining elements. But eventually, the array will become full if no elements are removed. So let's define the data fields we need. Here is our ArrayBag class in UML. The array bag that holds the group of objects is an array of the generic type T. The length of the array defines the bag's capacity. We can let the client specify this capacity, and we can also provide a default capacity. In addition, we want to track the current number of entries in the bag, so we can define a data field specifically for that number of entries. At least one constructor should be implemented before any class methods are called. You may leave that to be the default constructor inserted by Java, but in most of our data structures, we want to control the initialization of our data fields, so it's not common for us to use Java's default constructor, even when our class only has a default constructor. Our constructors must ensure all data fields have been properly initialized. In this case, it means initializing the number of entries in our newly created empty bag to 0. The constructor for this class must create the array bag. Notice that the declaration of the data field bag above does not actually create an array. Forgetting to create an array in a constructor is a common mistake. To create the array, the constructor must specify the array's length, which is the bag's capacity. The decision to use a generic type in the declaration of the array bag significantly impacts how we allocate this array within the constructor. The statement here is syntactically incorrect. You cannot use a generic type when allocating an array. Instead, we allocate an array of objects of type object. However, problems arise when we try to assign this array to the data field bag. This statement causes an incompatible type syntax error because you cannot assign an array of type object to an array of type T. That is, the types of two arrays are not compatible. A cast is necessary, but this creates its own problem. This statement produces the compiler warning. The compiler wants you to ensure that casting each of the entries in the array from type object to the generic type T is safe. Since the array has just been allocated, it contains null entries, so we know the cast is safe. And so we instruct the compiler to ignore the warning by writing a special annotation, suppress warnings unchecked, before the offending statement. But this instruction to the compiler can only precede a method definition or a variable declaration. Since this assignment does not declare bag was already declared as a data field earlier, we make one more revision to our constructor, creating a local variable to temporarily reference the new array and then assign that array to our bag. The process we went through to develop the statements for creating the array may have been a little bit complicated, but now that you understand why each statement is necessary, creating arrays of a generic type will be easier in the future. To help simplify our code, we can have any other constructors we decide to implement call this constructor. Now that our data fields have been decided and initialized by our constructors, we can implement core methods. Let's see which methods we may need to determine characteristics of the collection after it's created and been used. We need to determine if the bag is full. This can be a simple test that compares the number of entries currently stored in the bag to the bag capacity, which we can get from the array length. Now this was not part of the bag interface. It's a method we need because in our implementation we decided to use an array. Therefore, this will be a private method. Newly created bag should be empty, so we can use the method isEmpty to validate that a freshly created bag has no items. The number of entries data field should be 0. We can now check to ensure our bag is empty before adding items, and we can also check to see if it's full so we know when to stop adding. So it should be safe for us to implement the method to add items to the bag. When you add the first entry to an array, you typically place it in the array's first element, that is, the element whose index is 0. Doing so, however, is not a requirement, especially for arrays that implement collections. For example, some collection implementations we do can benefit by ignoring the array element whose index is 0 and using index of 1 as the first element in the array so the item's position is the same as its array element. Sometimes you might want to use the elements at the end of the array before the ones at its beginning. For the bag, we have no reason to be atypical, and so the objects in our bag will begin at index 0 of the array. As we add each item to the bag, it's placed in the next array element, and we increment number of entries. For our method implementation, we need to return a Boolean that indicates whether or not we were successful in our add. In this example, we'll initialize it to be true and only change it if we fail. If the bag is full, we cannot add anything to it. In that case, the method add should return false. Otherwise, we simply add new entry immediately after the last entry in the array bag. If we were adding to an empty bag, number of entries would be 0, and the assignment would be to bag element 0. If the bag contained 1 entry, an additional entry would be assigned to bag element 1, and so on. After each addition to the bag, we increase the counter number of entries. Finally, we return result to indicate to our client whether or not the add was successful. Another technique we can use to create this method is to stub out the method first. We create a Boolean to return and then return it. That's all. Since no item was added to the bag, the Boolean should be false to indicate nothing happened. Why do this? As you'll see shortly, when implementing an interface, all methods must be implemented before the class can compile. We don't always want to implement every method completely at first. And we shouldn't implement every method completely at first either. But to test the class, we have to have some form of minimal implementation. This is called a stub. Generally, a stub has just a return value that indicates failure of the function or has no meaning to the client. If the method is a void function, just braces are enough. Once other functions have been tested, we can complete the stub. In this case, if the bag is not full, we add an item and increment number of entries and set the result to be true to indicate success. Now that we're adding items, it would be helpful to have a better idea of the success or failure of our actions. We need a complete report on what is stored in the bag. The toArray method can provide us with that. Since we use an array to store our bag items, we could just return a reference to that array. It seems this method could be very simple. But even though this meets the explicit requirements of the ADT bag specification, it is a very poor programming practice. The array bag is declared private so that the data structure controls access to the array itself. The client should not be able to manipulate the data structure's data directly. Giving the client direct access to the array bag permits the client to change or remove elements. If the client does this, internal bookkeeping variables such as number of entries will not accurately reflect the number of items in the bag. This leads to what's called an internal inconsistency in the data structure. It destroys the integrity of the bag and can result in many hard-to-trace errors. It's a better programming practice to return a copy of the array or any other data field in the class. As we said earlier in implementing the constructors, since we need to create an array of generic type, we have to suppress compiler warnings, create an array of objects, and cast them to the generic type. We can then copy the entries from the array bag into this new array and return the array to the client. At this point, we have all our data fields, constructors, and core methods implemented. Before we can test our class, we have to stub the other methods in the interface. We can have getCurrentSize return -1. This would be a clear indication to the client that the method's not complete, since we'll never have a negative number of entries in our bag. The method remove can return null, which indicates the remove was not successful. And that's a fact because we actually haven't removed anything. Similarly, the method to remove a specific item should return false since the item will not be removed. The void method clear only needs braces. The method getFrequencyOf can return -1 to indicate an incomplete method. And the method contains can return false because it's not implemented. It can never determine if the item is in the bag. It's not important that these functions are not correctly implemented at this point. We want to ensure we have a small amount of completely error-free code in each so that we can focus our debugging efforts on the methods that we did implement, the constructors and core methods. In an earlier lecture, we discussed developing a detailed test for an ADT implementation, so here we just highlight the possible sequence of activities to test our implementation so far. To begin testing, we could create at least 2 new array bag data structures, one using the default constructor and one with a client-defined capacity. After creating the bags, we should validate that they are empty and not full. We then add items to each bag and use the toArray method to validate that the items we added actually appear in the bag. Finally, we could fill each bag to capacity and validate that it is full and not empty when the number of items added to the bag matches the capacity of the bag. We should also try to continue adding items to a full bag to validate that those adds fail. It's as important to test for failures as for successful activities. After successfully testing and debugging our core methods, we're ready to continue and implement additional methods in the array bag. Next, we will implement methods to give us the status of the collection and of individual items in the collection. The getCurrentSize method is a simple implementation that returns the value of number of entries data field. The method getFrequencyOf must iterate through the array bag and increments a counter each time an item equals the parameter that was sent as a target. We start with the parameter and entry to be the target and loop through each entry in the array, being sure not to go past the last entry in the array. We do not loop through the array elements that do not hold an item for the bag. We check to see if the current entry equals the parameter. If it does, we increment our counter, and then once the loop ends, we return the counter. The method contains has a different implementation since we're only concerned with whether or not an element is stored in the bag and not how many times it's stored. We initialize our Boolean to return was found to false, since at this point in the method, we've not found the item. Here we have a compound Boolean test. We only search through the array until we find an item, and we've not reached the end of the bag of entries. The earlier getFrequencyOf method always completes the loop number of entry times. This loop will terminate sooner if the item is found. If the current entry equals the target, we set was found to true since we found the target item, and so the bag contains that item. This causes the while loop to terminate also. If the item did not match, we increment the index and repeat the loop to check the next item. The final methods we need to implement are those that remove items from the bag. First, we implement removing an item, then all of the items. Last, we implement removing a specific item. The remove method must first declare an object of generic type T that we can use to store the entry that we're removing. We initialize this object to null, then if we're unable to remove an item, this value can be a signal to the client that no item was removed. If the bag is not empty, we then copy the last entry in the array into result and set the last entry to null. Setting the entry to null is a safety feature to clearly indicate that no item of value is stored in this array element. The order of these two statements is very important. If you set the array entry to null before saving the value in that array entry, you lose the data stored in that array element. After saving the item so we can return it and setting the array entry to null, we have officially removed the entry and can decrement number of entries to reflect this. The clear method is simple to implement if we use methods that we've already completed. We can loop, continuously removing items until the bag is empty. Because the method remove decrements number of entries for us, we don't need to worry about that here. Removing a specific item is the most complicated method we need to implement. Let's look at how it works. Here we have our array that stores the items in our bag. Our client asks us to remove a specific item from the bag. This is our target entry. This item is passed to us in the parameter and entry. We then compare that item to each item in the bag, starting at the first item. While comparing the target to each entry, we track the entry we're comparing using the variable index. When the target matches an entry, we remove it by copying the last entry in the bag into that slot. We then set the array element that used to hold the last entry to null and decrement the number of entries data field to reflect that an item was removed. Let's look at the code behind this. Because we need to search through the bag as we did in the method contains, we need a Boolean to indicate whether or not we found the item to remove and an index to track which item we're comparing to the target. Our while loop takes us through the array bag until either the target is found or we've reached the last entry in the bag. If the current bag entry matches the target, we set was found to true, copy the last entry into the position of the entry that matches the target, then set the last entry to null and decrement the number of entries to indicate that the item was successfully removed. So we have 4 specific actions we take when we do find an item that matches the target. If the current entry does not match the target, the index is incremented and we repeat the loop with the next entry in the bag. Finally, we return the Boolean was found to indicate to the client whether or not the target was found and successfully removed. The activities this method performs, searching the bag for a specific item and removing an entry, are shared by the contains method and the other remove method respectively. A good optimization for this class would be to create two private methods that could be shared, one with contains and the other with the first remove method we covered.